So we're not going to go into too much depth. We're just going to cover principles 7 through 10, I think is what it is. Yeah. Very, very simple principles. Like any of the math that we've been doing so far, the biggest piece to this is when do I use this principle, or how do I know which principle to use? So that's just going to come with time. If you're going to be a machinist, if that's your goal, the principles of geometry is something that you just got to practice. You'll find ways to use it, but more so you'll come across prints from time to time where there is some missing information. You got to solve something, and if you remember your principles of geometry, you'd be like, oh, that's easy. I can figure this out. But it does come with time. No matter how you feel about math, if you want to be a machinist, you will have to be good at math. So maybe I should ask, can everyone access the document while I'm talking, or can you only access the screen that we're on? Like, does anybody need me to redraw everything? I just want to know. It'll save me some time if not. All right.
No, I'm on mobile right now.
Okay, so you need to see everything.
Yeah.
Okay, that's okay. That's all right. That I can handle that. Okay, so what I'm gonna do is I'm gonna see if this works. Copy, and does it let me paste? Oh, it does. Look at that. Okay, so let's start with this. So here we're talking about we're going to talk about principle number 7. So how principle 7 works. So the description here is two triangles are similar if their sides are respectively parallel. So the one thing I need you to understand is about what a similar triangle is. So here we have two triangles, triangle DEF and ABC. When we refer to triangles being similar, you could say that the triangles are the same. The wording is just not accurate, because really this triangle, this green triangle, and this blue triangle, they don't exist in the same space. So they're not the same triangle, they're individual triangles. So we call them similar. So in other words, they could have the exact same geometry, like angle E is the same as angle B. Angle D is the same. Oh, you guys can't see my mouse, can you? I forgot about that. Okay, so we could say that angle DE is the same as angle B, and angle D is the same as angle A, and angle F is the same as angle C. So if those angles are all the same, these triangles are similar. And the other way is if this line, so we'll maybe just go back. Which one is it? This one here. All right, so I think it's undo. Hold on. Okay, so the other way to do this is examining the lines themselves. So let's go to line AB is parallel to line DE. So those two lines are parallel. Line BC is parallel to line EF, and line DF is parallel to line AC. So two triangles are similar if their sides are parallel. Okay, so another way you could think about this, if you want to know if these triangles are similar, these parallel lines will tell you, yes, in fact, they're similar. So what does it mean for them to be similar? It's kind of like them being the same, right? If I took that green triangle and I pinched it open until any one of these lines overlapped a line on the triangle on the outside, as soon as line DE overlaps AB, then line AC will be overlapping DF and EF will be overlapping BC. In other words, if I pinched it open, those triangles would sit perfectly on top of one another. And essentially, you wouldn't be able to identify two triangles. It'd look like one. So we need to understand that similar triangles are useful because whatever you solve in one triangle translates over to the other. So I could have this triangle DEF over here somewhere. I could have it sitting over here, and I could, let's just pretend these are the same. I could have an angle here. I might know that angle, right? It might be 10 degrees. And I might know this angle in this triangle, angle D. I might know that that's 35 degrees. So if I said triangle ABC is similar to triangle DEF, what is angle E? Right? So I've only got one angle here, but I have the other angle here in this triangle because this angle is the same as that angle. This angle right here is the same as this angle. So I have two angles of 3, and I know how to find the last one. So similar triangles are important to know because you may be able to take information off one and apply it to another. Okay. All right. Excellent. Let's go to, I love this copy paste. This is beautiful. It's going to make my life easy. All right. Let's do this one. Maybe it'll make it easy if I can grab it. There it is. All right. So let's try this one here. So this is an example of principle 7 as well. So the first one we talked about, two triangles are similar if their sides are respectively parallel. Now we're talking about two triangles are similar if their sides are respectively perpendicular. So what I did when I sent you this assignment, I like to color code stuff to make life easy. So this orange triangle, imagine I took this blue triangle, I made a duplicate of it, I lifted the duplicate off and I rotated it 90 degrees and I set it back down again. That's what you're looking at here. Essentially, this line, this baseline of this blue triangle, I've rotated up like this, and it's now this line, okay? So if I saw these two triangles and I wanted to know, are these similar triangles? The way for me to solve this is if I can make 3 90-degree angles between the two triangles, then those triangles are similar. So I'll show you. The first 90-degree angle is here. Okay. The second 90-degree angle is here. And the third 90-degree angle is here. So if I wanted to know if these triangles were similar, I should be able to intersect one line of one triangle with another line of the second triangle and create a 90-degree angle between them. Now, imagine if these triangles were not similar, then let's take, for instance, this here. Let's imagine that this line, right, came out like this and then carried on this way, okay, and carried on like this. This right angle would still be true, right? That right angle here would still be true because it's this baseline and that blue triangle. This one would still be true, but the problem is that this is no longer a right angle, right? This line is out here, so I would have to try and figure out if I could create a right angle out here, but it wouldn't be true because this intersection here would not intersect this line at 90 degrees. The problem is that when you're trying to find this information, you have to have certain knowns, right? So you wouldn't be expected to look at two triangles and say, I wonder if those triangles are similar. They must be. They're so close. The expectation here isn't that you can look at this orange triangle and know that it is a similar triangle. I wouldn't expect you to be able to look at this and say, oh, Yeah, those are similar triangles. I got this. How do you know? Well, it comes with a description of the problem. So if we were to approach a problem like this, we had this drawing or this illustration, and I said, solve angle whatever this is. Okay, I want to know what this angle is here. And you have this angle of the blue triangle, and you have this angle of the blue triangle. Okay, and I want you to solve this angle. I would have to tell you that triangle A and triangle B are similar triangles. It's the only way that you're going to know. Now, how am I going to tell you that? I'm going to tell you that by putting the three 90-degree angles in there. So I could say triangle ABC and triangle DEF are similar triangles. Solve for the unknown information. Or I could simply put three right angles here and say solve angle B. You should know by seeing those three right angles that these are similar triangles. Okay, so you won't have to try and figure out if a triangle is similar to another one. You'll be told. You just have to be able to do the math that applies. So you have to understand how it being a similar triangle helps you to solve it. Okay, clear as mud so far? All right, good. If you got questions, feel free to jump in. Otherwise, I'm going to keep moving through this. The next example I want to give you guys is the third example of Principle 7. So this one's kind of easy. So within a triangle, if a line is drawn parallel to one side of a triangle, the triangle formed, so this new triangle right here, okay, the triangle formed is similar to the original triangle. So really all I've done is I've taken line BC, I've made a duplicate of it, and I've moved it parallel to it further into the triangle, right? And then I just cut it off here and here as far as length goes. But really this is the same, if I just took this line and I redrew it right here, nice straight line, okay, and these two lines are parallel, then this new triangle, triangle AED, is similar to triangle ABC. And what's interesting about this, why similar triangles are also important to note, is that, I'm just going to erase these as I speak here. It's all about the angles, right? In geometry, this is what matters when it comes to similar triangles. So these three angles here, combined, they equal 180 degrees, right? We know that. But this line, just because I move this line in a straight line, right? I make it parallel. ED is now parallel to BC. This angle doesn't change. This angle stays the same as this one. And this angle stays the same as that one. No matter where I redraw this line in this triangle, no matter where I put it, the further along I move it, as long as it is parallel, okay, the angle in here does not change all the way down. It stays the same. So we're not changing the form, the geometry, by lengthening our lines. We change our geometry by changing where the lines point, right? Where they end up. So again, important to note, because if you decide to carry on in the machining world and you take your apprenticeship, when you get into the third level apprenticeship, hopefully, I know I did, but hopefully your math instructor will teach you some complex machine application math. And in that math, what it teaches you to do is to look at a part that needs to be produced. And when you look at that part, it wants you to solve a length Perhaps it's a tool ball, a tooling ball, and you have to know to 4 decimal places where that tooling ball is located from the 0 position in the machine. So for you to be able to solve that, there's some information on the tooling ball assembly that you'll need to know, and where the part sits on the mill. And you're going to have to be able to carry geometry, right, of what you know, and be able to identify this angle. If I draw a parallel line further down myself, maybe that line doesn't exist, but if I recreate that line parallel at a point that I need to solve, I at least can bring the geometry with me. At least I have an angle to work with. And that's the type of math you'll be using. You're going to be applying all these principles in different ways. Now, you may not remember what the principle is, but you'll remember what it does. And this is one of those ones we use a lot, right? In Principle 7, we use this a lot so that we can redraw, resketch lines parallel to other lines that we have information on, and carry that information to another part of the print. It's so useful, you know. And the sad part is that a lot of machinists, they've strayed away from caring about the problem solving part. But I think I've told you guys before, you know, I could hire 1,000 people to push buttons, you know, in my own shop, but I'd rather hire one that can troubleshoot. You know, I'd rather have one that can figure out their problems, or at least they try to figure out their problems. That's more important to me than just having someone that's a yes man. Finally, the last piece of Principle 7 here, I think it's the lengthiest one that we have. So I'm going to just copy this over. Oops. Okay. So Principle 7a was 2 triangles are similar if their sides are respectively parallel. 7b, 2 triangles are similar if their sides are respectively perpendicular. And C, Principle 7c, within a triangle, if a line is drawn parallel to one side, the triangle formed is similar to the original triangle. So D part, in a right angle triangle, if a line is drawn from the vertex of the right angle perpendicular to the opposite side, the 2 triangles formed in the original triangle are similar. So let's put that into language we understand. So I'm gonna just draw real quick a right angle triangle-ish. Okay, there's my beautiful right angle triangle, and here we are here. So this principle says that if a line is drawn from the vertex of the right angle, so if you don't remember, this is your right angle. This is the vertex where this length, side length, and this side length meet. Okay, that's your vertex. So if I draw a line from the vertex of the right angle perpendicular to this side, which means create a right angle, right? This line has to intersect this line at 90 degrees. So if I start here and I draw a line 90 degrees to this hypotenuse, the 2 triangles, triangle A, triangle B, that I just created, they're similar triangles. Okay, so that means that this angle here is the same as this angle here. We know that's true because I just divided this in half, right? I took this 90 degrees and I drew a line at the vertex. That makes this and this 45 degrees. Now, no matter what this angle here is, right? This could be 30 degrees, right? Oh, I guess not. This is 90 now, or that's 45. So I guess that's not true. This now has to be 45 degrees in this example. Okay, so I draw 90 degrees here. This becomes 45, and this becomes 90, right? 90 and 45. So these 2 triangles are now similar triangles. The angles are the same on opposite sides of this line that I drew from the vertex to the base of the triangle. Okay, so that's all I've done here. I've just shown that if we draw in that line and we create right angles, we draw it perpendicular to this hypotenuse, we get a right angle obviously on each side. If there's a right angle on this side, there has to be one on this side if we're talking about the same hypotenuse. Okay, so those principle 7 is not complicated. You just have to kind of, when you look at a problem, you're going to get some, I think we have, how many do we have? 16, 9, I think we have 9 questions for you guys today. So all of your questions, all your assignment questions are going to be based on, and I'm just going to say this because I know you're smart enough to do it. I'm going to say it anyway. Open up the lesson plan for tonight, the one I'm working from, the one I emailed you earlier. All your principles are drawn out and they're all explained. So when you get a math problem, look at the triangles here and see which one best matches what you're trying to solve. And then at least it'll help you just quickly identify which principle that you want to use. And before we wrap up our recorded lesson, I'll give you a couple of quick examples of what you might find on your assignment. Okay, let's talk about principle 8. So in principle 8, now we're talking about, we're going to talk about this isosceles triangle. So I'm going to bring it over. Okay, principle 8 says, in an isosceles triangle, an altitude to the base bisects the base and the vertex angle. So remember, an isosceles triangle, the length of AC, the length of AC equals the length of BC, right? AC is the exact same length as BC. And angle A is the same as angle B. So that's what will make this triangle isosceles, right? The only thing that's different is this angle up here. So this does not have to be a right angle. In principle 7, we were talking about a right angle, drawing a line from the vertex to the base in a right angle, but this doesn't have to be, right? This could be 30 degrees, this could be 30 degrees, which gives you 60. So you know that the angle up here would have to be 120, right? This complete angle would have to be 120. So in principle 8, that's what we're talking about. This is not 90 degrees. It's anything other than 90 degrees, okay? So if we were to take an altitude is the line that we draw from the vertex to the base, okay? So you have to draw it perpendicular. This altitude has to be drawn perpendicular to this line so that we create a 90-degree angle here, okay? So let's give an example here. I think you probably get this, but I'll just show you this here quick. Let's imagine, oops, what's going on here? Come on. Okay. Let's imagine that this is 35 degrees and this is 35 degrees, okay? And so that being 70, this included angle has to be 110, right? 110 degrees. Okay, so AC equals BC. So we'll say that this side is 10 units long, therefore that side is 10 units long. Now I can identify this as an isosceles. These two lengths are the same and the two angles at the base are the same. Now if I take a line, an altitude they call this line, and I draw an altitude from the vertex to the base and create a 90-degree angle. Now triangle A and triangle B are similar triangles. If I actually took triangle B and rotated it right around this altitude and overlapped B on top of A, these triangles would overlap perfectly, right? Those triangles are similar. Now, the second part of the principle number 8 is taking an equilateral triangle. So we talked about a right angle triangle in principle 7, drawing an altitude from the vertex to the base. And then we talked about an isosceles triangle just now with principle 8. And now we're going to talk about an equilateral triangle. So in an equilateral triangle, an altitude to any side bisects the side and the vertex angle. So if this were an equilateral triangle, which it doesn't look like I drew it very well, but you remember equilateral means that AB, line AB is the same as line BC, which is the same as line CA, right? The length of each of these lines are all the same. That means that this is 60 degrees, this is 60 degrees, and this is 60 degrees. So an equilateral triangle, note this, because in your math today and in future problems you're going to face, if you right away know what kind of triangle you're dealing with, you can solve some of it without even using a calculator. If you look at an equilateral triangle, the angles will only ever be 60 degrees, right? The angles have to be the same, and any triangle totals 180 degrees. So you divide that by 3, it's 60, 60, and 60. In an equilateral triangle, that's always the case. So I could draw a line from here to here, or I could draw it from here to here, or I could draw it from here to here. 90 degrees, 90 degrees, 90 degrees, right? So whatever vertex I choose, if I draw a line from the vertex to the line on the opposite side at perpendicular to it, then principle 8 applies. It says in an equilateral triangle, an altitude to any side bisects the side and the vertex angle. I really, really hope that you guys are able to take a level 2 machinist math, because we get into circle math. We're only going to touch on it a little bit, but when you start seeing how simple geometry questions can be just by identifying the principle, it would have made high school easier. It would have made learning math a little bit more fun if you could see how it works and how it applies specifically to problems. Everybody's favorite, principle 9, is the Pythagorean Theorem. So the Pythagorean Theorem states that the square of the hypotenuse is equal to the squares of the other two sides. So you'll remember this, right? A squared plus B squared equals C squared, right? That is principle number 9, the Pythagorean Theorem. That's not supposed to be an R. Okay, the Pythag theorem. Okay, Pythagorean theorem. There's got to be an R in there too. All right, so how does this work? So it works with a right angle triangle. So let's take this triangle, right angle. Okay. What that means is I can just to be clear too, in the Pythagorean theorem, C is always the hypotenuse. Okay, remember that. C is always the hypotenuse. What is the hypotenuse? It is the longest side of a right angle triangle. It is always directly across from the 90-degree angle. Okay, so when you're solving Pythagorean theorem, you're solving for C, but maybe you're solving for A. Maybe you're solving for B. Well, how does that work? How do we use the Pythagorean theorem to solve for these things? Well, we go back to basic algebra And that's not to scare you. That's just simple. Let's do an example. So in this right angle triangle, the length of A, okay, A equals, let's call it, say, 10. And the length of B is 8. Okay, so this length is 8 units. This height is 10 units. What is the length of C? So in the Pythagorean Theorem, it states, and you can call this side A or this side A. It doesn't make any difference, right? So A squared plus B squared equals C squared. So we solve it by plugging in the numbers. I'm going to call the height 10. So 10 squared plus 8 squared equals C squared. 10 times 10 is 100. So 100 plus 64 equals C squared. Now, what we need to be able to do here, I know some of you know this, and that's great, but some of you may not. So what we need to do here is figure out what C squared is. So the first thing we got to do is this. We're solving for the unknown, which is on this side, right? Technically, what we're trying to solve is C. So squared needs to be moved over to the other side of the equal sign. So if you remember your algebra from high school, whenever you move something to the opposite side of the equal sign, you do it by creating its polar opposite, right? So if it's squared on this side, it's the square root on the other side. So I would rewrite this formula as the square root of 100 plus 64 equals C, okay? So what we need to do is figure out what the square root of 100 plus 64. You need to be able to add this together before you find the square root. So 164, obviously. And then we need to do the square root of that. Now, where is that on my calculator? That is squared. That's interesting. It's not on here. Okay. So then I will have to do it on. I wonder if that's just squared. Let me do it on my calculator. So on your scientific calculator that you're going to use, probably, right? What you're going to do is you're going to type in. On mine, I have to access square root. You can probably, let me just see if I can get the reflection off the screen here. There it is. You see square root up in the upper corner there. So square root, and then type in 164 in your calculator like that, and then hit equals. So I noticed that it's the same as the one on my computer, right? Oops, let me move. I got to move the opposite direction of what I want because I'm reversed. Okay, so on the calculator on the computer, you can see the mouse is hovering over this button right here. I hope you can see that. That's my square root button on the computer if that's how you're going to do it, okay, right here. So the answer, C equals, right, C equals, we're just going to round it to whole numbers. C equals 13 because it was 12.8, right? So that's how we would use this formula, principle number 9, to solve unknown. Let's do a second example, but let's do one real quickly on having C. So here's our triangle, right angle. The length of C, we'll say, is 20. And we'll say this length here is, let's say 12. We'll keep everything nice and even and simple. Okay. So Pythagorean theorem says that a squared plus b squared is c squared. So we'll rewrite it. A squared plus 12 squared equals 20 squared. Okay. It keeps the formula true. We just put the information where it belongs in the formula. We know we always have c squared is always the hypotenuse, so it's always here, right? So what do we know? Well, we know if we add this plus this, we get this. So if we subtract one of these two from this, we'll get the other, right? So if a squared plus 12 squared is 20 squared, then 20 squared minus 12 squared has to equal a squared. I like to just keep it simple, like saying, 2 plus 3 equals 5, right? Same algebraic expression. Something plus something equals something else. So plug in something easy. 2 plus 3 equals 5. How would I rearrange this to find this unknown? If I didn't know what this was, I would take the 5, I would subtract what I do know, and it would tell me what the answer is, right? So you just sometimes just simplify your formulas, plug in information that's easy to solve so that you can see. Now, algebraic expressions, it doesn't matter what's here. If you're adding it to something else, make the numbers simple, right? So something plus something equals something, make it simple so that you can see how would I rework this to solve for unknown information, okay? So how am I going to rewrite this? Well, I'm going to rewrite this like this. First, I'm going to solve 20 squared, right? So 20 squared, I need my glasses. I should know that. What am I doing? 400 minus 12 squared. I should also know that. Sorry. 144 equals a squared. Okay, so I want to move squared to the other side. So I say the square root of, and if you want to, you can put brackets. Brackets means do this first, right? Right, so that you remember that you got to obviously solve that before you can find the square root. 400 minus 144 is 256. So what is the square root of 256? So square root, and the answer is 16. So I know that A equals 16, right? And that keeps the Pythagorean theorem true. 16 squared plus 12 squared is going to equal 20 squared, okay? All right, last one I want to show you. We'll do this very, very quickly. Some of you may not have learned this. There's a formula for principle number 10 that makes life easy. I'm going to actually copy this just to make it even easier. Copy and paste. So in this figure here, we have a 5-sided part. And in that 5-sided part, let's say, for instance, we want to know what angle A is. And we know that this angle here this is the illustration I used in the assignment I gave you, or in the lesson plan. Okay, we have these angles here, and I want to know what angle A is. We're not talking about triangles anymore, right? We're now talking about polygons, other polygons. So principle 10 says the sum, okay, or otherwise, if I add up the angles, the sum of the interior angles of a polygon of n number of sides, so fill in the blank, is equal to this. So how do I solve? N minus 2 times 180, okay, will tell you what the total degrees of the polygon is. Okay, so think about what we're talking about. A triangle is always 180 degrees. But as I add sides to a polygon, the angle increases. And this should make some sense because triangles and circles are related, right? A triangle is a 3-sided polygon. What's a circle? Mathematically speaking and scientifically speaking, a circle is a multi-sided polygon. There is no perfect circle, right? It's made up of maybe millions of tiny microscopic straight lines. it's a geometric shape that is a polygon because you cannot make a true arc, scientifically speaking. So as I add sides to this polygon, more and more and more sides, it gets closer and closer to a round part, right? And when we get into circle math, you're going to see how relative this lesson in geometry is, because pi, the formula pi in a circle comes from triangles, right? And we'll teach that when that time comes for you. So I want to know, well, what is the total angle in here? Because without the total angle, I can't figure out A, right? So this is the formula, n minus 2 times 180. What does n equal? Well, n is the number of sides or number of angles, right? Because they'll be the same. Okay, so how about we just call it number of angles, and then you won't forget. Okay, number of angles. Okay, so how many angles are there? 5. So our formula can be rewritten as 5 minus 2 times 180 equals total angle. Okay, what's important to note here is you have to understand, what am I trying to solve? I'm trying to figure out the total angle. And the only way this works is if I figure out how many angles I have to work with. To do that, you have to make sure that you solve this first, because BEDMAS, the rules of BEDMAS says that brackets happen before anything else. So if I specifically need to solve this first, I'm going to put brackets around it. Because otherwise, brackets, then exponents, and then division and multiplication, the order they come. So if I don't put brackets on here, technically I'm supposed to solve this as 2 times 180, right? And then 5 subtract whatever that answer is. And that wouldn't be right. So we need to make sure we solve this first. So make sure when you get these questions about solving the total angle in a polygon, make sure you put brackets around your n minus 2. Now we end up with 3 times 180, right? 3 times 180, what does that equal? 540. Again, another thing I should know. I've only done this 9 million times. The total angle in here is 540 degrees. So if I want to solve angle A, then I take 540, my total angle, minus 115, minus 80, minus 100, minus 75, and that equals A. So I just subtract the angles I know from the total angle, and it leaves me with A. So for this week's lesson, you can imagine there's actually a lot more to this, but I don't want to complicate this. I just want you to be able to see the principles, how you can apply them, and then be able to identify when you get your assignment, okay, this triangle or this figure looks sort of like, oh, this one in principle 7D. And then you have a place to start, and you know how to solve that.